This video is for November 7th, November 8th. We're looking at the fundamental trigonometric identities, starting a unit where we will use these identities to simplify expressions and verify other identities moving forward. Today we won't see too much application. We didn't see much application. What we saw instead was, what I like to say is we built our toolbox. So we didn't have anything in our toolbox yet, but after today, after looking at all of our different tools and developing them, then we'll see how we can use those and apply them in next class. So there's not going to be much application. As we move forward, you'll see how we're going to use these. So let's get started though. Here we call these reciprocal identities. And so for example, I'm going to do cosecant. If sine is opposite over hypotenuse, then cosecant, because it's the reciprocal of sine, would be hypotenuse over opposite. So I'm going to suggest that the cosecant, we could also write that as 1 over sine. U is just our variable. It doesn't matter. It's just a variable. And then let's check this. So if that's true, if this is true, then we should get hypotenuse over opposite when we simplify. So I'm going to put 1 over opposite over hypotenuse. If we're talking about over, we're talking about division. So we could really write it as this. And then we know that if we're multiplying or dividing by a fraction, we really multiply by the reciprocal. And 1 times anything is itself, which is true for cosecant. Because if sine is opposite over hypotenuse, then cosecant would be hypotenuse over opposite, which is what we want. And so we can fill the rest of these. The sine, the reciprocal of sine is cosecant. So we can write this as 1 over cosecant u. Cosine, the reciprocal is secant. Tangent, the reciprocal is cotangent. Secant and cosine, and cotangent and tangent. So those would be our reciprocal identities for our 6 trig functions. So the idea being, if we were to see cosine or even secant in a problem, what we could do is replace secant with 1 over cosine, because those two things are equivalent. Okay. Next one, I'm not going to really talk too much about. It's called our even-odd identities. I'm just going to give you those here. Essentially, sine and cosecant, those are what we call odd functions. Cosine and secant are even functions. And tangent, again, is an odd function. Same thing with cotangent. Because sine and tangent, cotangent, cosecant are odd functions, then the negative, if there is a negative inside of the actual function, what we can do is move that negative and move it to the outside, making that u positive. Okay, so that is what creates an odd function. Cosine and secant are even functions, which means that the negative here actually goes away. We don't have to deal with the negative because they are even functions. Yeah, I'm not going to explain too much about that now. We'll talk more about odd and even functions actually next semester. It's just another tool in our tool belt. Now we get to proving identities. So here we have this triangle, and the idea is we want to write the Pythagorean theorem in terms of sine and cosine. Well, in order to do that, we need to use the definition for sine and cosine. Like for example, sine of u is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So the idea is we have to write, if we're doing this, we have to write the Pythagorean theorem in terms of opposite, adjacent, and hypotenuse. And the way we do that is let's call this angle u. Then that means that this would be the opposite, this the adjacent, and this the hypotenuse. And using Pythagorean's theorem, with this triangle, what we would get is the opposite squared plus the adjacent squared equals hypotenuse squared, right? A squared plus B squared equals C squared. And in class, I gave students time and talked about what could we do here to write this in terms of sine and cosine. And some students said, well, hey, in both sine and cosine, the hypotenuse is in the denominator, which means somehow if it's in the denominator, we need to think of an operation that we can do to both sides to get that in the denominator. And ultimately what we decided on is, what if we divided both sides of the equation by hypotenuse squared, which we can do. Then this would become 1, and we would have opposite squared plus adjacent squared over hypotenuse squared. And then we can do something here. If we have addition in the numerator, addition or subtraction, we can do what I like call break off the fraction and write it as two separate fractions. So what it means is we can write it as opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. I can break off the fraction as long as I divide both of these by hypotenuse squared, which I did. Now we have opposite over hypotenuse, which is sine, but they're both squared. And so because they're both squared, that's going to become sine squared. Similarly here, we have adjacent over hypotenuse, which is cosine. They're both squared, so this becomes cosine squared equals 1. And so this is our first Pythagorean identity, that sine squared plus cosine squared equals 1, using this. This here is a strategy to separate the fraction going from here to there. That is a really helpful strategy with a lot of problems that we're going to deal with moving forward. So if you want to put a star next to it, make a note on if we have addition or subtraction in the numerator, we can split up the fraction. That might be a good thing. But so far what we've done is we've looked at reciprocal identities with our 6 trig functions, the even odd identities, and we've proven one of the Pythagorean identities. In the next video we're going to look at the other Pythagorean identities. There's 2 more, and then we'll look at the co-function identities, and that'll probably be the end of the videos for today.